Dr. Abir. He is now with the Max Planck. He's now a postdoctoral researcher in the Max Planck Institute of Software Systems at MPI at Kaiserslautern, Germany, since January 2018. Prior to this, he did PhD in 2018 from IIT Kharagpur, where he was associated with the Complex Network Research Group. He did his BTech and dual degree MTech from IIT Kharagpur Electrical Engineering Department and Control Engineering Department. While doing PhD, he was a Google India Research Fellow 2013. So Abir's main research is in modeling, learning, and control of network dynamical processes. He's also now working on deep learning on graphs, such as deep generative random graph model, deep reinforcement learning of network processes, etc. So today, Abir will give a talk on deep reinforcement learning of marked temporal point processes.
So, hello, okay. So, thanks Professor Sharkar for introducing, and Professor Sundaram for inviting me, and thanks everyone for showing up. So, this talk is about controlling marked temporal point processes using deep reinforcement learning. So before going to the details of temporal point processes, I will give a bit of motivation. So in practice, we will see there are a lot of phenomena where discrete events are involved in continuous times. For example, when people post tweets in Twitter, or people post reviews in Amazon, you will find that they are posted in discrete events, like messages at some point of time. And these events doesn't appear in discrete time steps. That is, they don't appear uniformly. They more or less appear like in an asynchronous fashion. So apart from these online actions, we'll find other examples of this sort of discrete events in continuous time, like epidemic process, that people can get infected at random times in random moments in continuous times. Also, there are examples like financial trading and human mobility dynamics, when people change their cities or people even change their countries at several, as in terms of discrete events. And there are a lot of processes that are involved behind this process. And these events are mainly observations of a very complex dynamical processes. And interestingly, they vary in a wide range of time scales. For example, if you consider stock trading or news spread in Twitter, they are basically very fast in comparison to if you consider ride sharing requests in Uber or Ola or flu spreading. And if you think of reviews or sales in Amazon, that is a little bit slower. And even there are shorter events, the events that evolve in shorter, larger time scales. For example, article creation in Wikipedia, or how an user reputation changes in Quora. So they generally evolve in a very longer time scale and so on. So let's consider one example. Consider this network. Say this is a very small network between 5 users. And say Bob and Christian posts a message at 2 times, and then followed by Beth, David, and Joe. So you can see that these events are more or less, asynchronous events, but they are taking place in continuous time. So the inter-arrival time between these two messages are very important. And virtually this takes place over the network, so this information propagates over time, and the whole information propagates in a network. And you can see that they have a very long-term impact in the offline world. So another example is knowledge creation in Wikipedia. So you can see that if some person posts an Wikipedia edit, and then it can be false, and other people can add or refute that comment and change this post. So even in Quora, you will find that people post, and and the other people tries to answer those questions. And all these processes basically are asynchronous processes, and they change over time. Now the question is, aren't these events are just time series? The question is, you can think of that there is a continuous process going on, and there are just samples of this continuous process. But there are a little bit difference. And the difference is that this is not typically the time series, but the discrete events in continuous times. So one can think of that, well, what if I just convert this entire discrete events, the stream of epochs into discrete times in like aggregating events in epochs. So then there are several problems. So the first problem is how long is each epoch? And the second problem is once you have decided the length of the epoch, you have to think that how to aggregate these events. Like for example, if you have decided like, okay, I will take a length of the epoch like in 10 days, then how to aggregate these events? Should it be mean or median or some nonlinear function? So you don't know. And then suppose you train this model with some length of epoch and then some aggregated behavior, then in the test set you can certainly find that there is no event in some epoch. So how to define that how to define information in that particular epoch? And what about the other time-related queries also for that epoch? So those questions are important. So the framework of temporal point process gives a very natural representations for this kind of phenomena to tackle this kind of shortcomings. So what are marked temporal point processes? So marked temporal point processes are basically as a particular type of stochastic process or random process that consists of a discrete event localized in continuous time. So it can be represented as a history up to some time t, and the history consists of event that contains a tuple which consists of the time t at which the event has occurred, and some information which is called mark associated with that time. So and this mark can be, for example, sentiment associated with a particular message, the likes or dislike associated with a particular message, or something, even some non-numerical quantities, something, anything that can be well defined with respect to that particular event or the context. And these TIs are defined in continuous time. And sometimes these marks can be even like mixed. For example, they can be a discrete and continuous. There can be a vector that is represented as discrete and continuous signal output. So in the context of reinforcement learning, what we are trying to do here. So you can see that there is a, for example, you can think that there is a timeline of a particular user. For example, in social media, you can think that in this timeline, people are making posts. So this brown line can be thought as like a timeline of an agent, like the posts of an agent. And this agent is trying to maximize some reward. And this agent can perform an action, yj, that is a mark associated with that particular agent at time tj. And the environment provides some feedbacks. And the reward is calculated at each episode. Like for example, in the traditional reinforcement learning, you can think that the reward is always associated with the state. But in many cases, at least in this work, we are assuming that reward is calculated at the end of each epoch. That is, at each state you don't calculate the reward, you can assume that the reward is 0, but the reward is calculated at the end of each episode. So the reward is obtained in the final. So an example of this kind of process is when to post problem, the problem where suppose you are an advertiser and you want to elicit more attention from the users, and your objective is to try to gain the visibility of your post as maximum as possible from the other people. So basically, the thing that is in your hand is you can post tweets, but the question is when to post so that the visibility is maximum. And at the end of the process, the average rank will be calculated, and that will be defined as a reward. So you can think that, so this AT is basically the actions that defines the times of your post that you want to determine that at which time I should post. And then the feedbacks that you are getting is the rank of your post and the other people's post and the posts at the time of the posts of other people. And at the end of each time, the reward is being calculated. And another interesting example of this marked temporal point process is spaced repetition. Suppose you are going to learn a new language and you go to Duolingo to learn new words and so. So the Duolingo wants you to teach something. So he will give some word, you will remember that thing, and again they will test you So they will check whether you quickly forget or not about that particular word, and then it will give you new word to learn. So the idea is that you are going to suggest Duolingo to post the words or the schedule, the frequency in such a way that the learning ability is increased in longer time, or your forgetting thing gets decreased over a large amount of time. So here the test score is here the test score is calculated at the end of the course. So you can imagine that the Duolingo gives you a 14-day course, and they will give the score after 14 days, like at 15th and 16th, naturally what they do. So what they do here, so for example, you are trying to give some word, so they try to give you some word to remember at certain point of time, like say for example some 9:15 a.m. or 9:20 a.m. at some point of time, and they try to record that whether you actually remember correctly or not. And interestingly, here you can see that this feedback and actions are quite synchronous. Although these actions are basically asynchronously distributed, but whenever whenever Duolingo posts the word, that gives you the test, and that by doing that they understand whether you have understood, you have correctly remembered the word or not, and therefore these actions or feedbacks are basically synchronous. So there are certain nuances with this setting, and in the earlier setting, the actions are asynchronously distributed, that the feedbacks are asynchronously distributed, and both the actions and feedbacks are also asynchronously distributed. Here the case is a little bit different. So now the question is, how to optimize the agent strategy. So the feedback process can be complex or unknown in general, and the reward function can be arbitrarily complex. So in general, in these cases, there is no closed form solution. So you don't know the dynamics, that is the environment, what kind of feedback you are getting. At the same time, you don't know, the reward function is arbitrarily complex. So they cannot be quadratic all the time, and they cannot be linear. They can be arbitrarily complex. There can be some linear, there can be some integral of some quantity or some even complicated functions. And you can certainly apply the existing reinforcement learning techniques, but the problem is that the action or feedbacks are asynchronous here. And the state of the process is very difficult to determine. So going there, first I will introduce the representation of marked temporal point process, that how we represent this kind of phenomena. And then I will describe the reinforcement learning model specifically designed for marked temporal point process. And then I will describe the policy optimization and the evaluation. So this is a typical thing of marked temporal point processes. So here we represent as marks and times, as I have said, given by events, where an event consists of a time and the marks. And we model the marks and events times separately. So for example, the time is characterized by an intensity function. So you can think of some renewal process like a Poisson process, where the event that will the probability that an event will come in an infinitesimal time interval between time t and t plus dt is infinitesimally small. So most often you will find that a person is not posting in Twitter. So the probability is very small. And we try to model this lambda star t as the intensity or the rate of the event, and basically we try to parameterize this lambda star, which has a very intuitive meaning. And somehow it gives you an urgency of act. So suppose in the context of viral marketing, you see that the ranks of your post is going down very swiftly. That means that you are losing your visibility immediately. Then that means that you should post immediately in order to gain your visibility. At the same point of time, in the space repetition problem or this language platform problem, suppose Duolingo observes that you are forgetting very quickly, then the Duolingo has a more urgency to give you the same word that they have given you to test earlier at a higher urgency. So the time of events can be characterized, as I've said, by this intensity function. And this intensity function can model several behavior like self-correction or bursty behavior. So for example, if you go to Twitter, you will find that whenever a person posts in Twitter, there is an urgency of post by other followers, right? Because of follow-up or giving answer to that particular question. So by that, this rate can model the self-correction. And in general, this rate is a stochastic process. For example, in general, in Poisson process, the rate is constant. In inhomogeneous Poisson process, the rate varies over time. But the problem here is that you can see that whenever you post a message in Twitter, that changes the immediate rate of other people surrounding you. So depending on your behavior of post or message posting behavior, which is a random, the intensity of the posts of other user changes. So that directly affects the intensity. As a consequence, this intensity is also a random variable here. So it's a doubly stochastic. So the intensity stochastically determines when to post, and the intensity itself is stochastic quantity. So there is some kind of doubly stochasticity is involved here. And fortunately, we can explicitly write the probability of the set of events, set of time of events in a nice expression. So it's a product of this intensity. So this is basically I would say this is a likelihood, not the probability itself. So this basically is a product of the intensity values that said that at each point of time, the likelihood that an event will happen, and this exponential term is called the survival function, and it characterizes that the probability will not happen anytime other than these TIs. So it's an integral over all the time intervals in between the inter-arrival times. And one can think that if you find this lambda is basically a linear function of some known features, and one can surely show that this if you take the log likelihood of this thing, you will get a convex function. But the problem is that here we'll not consider this lambda is the linear thing, because we want to try to model a generic setting, and there will assume no parametric representation of lambda. And then the next question happens that, recalling the characterization of mark temporal point process, it consists of both time and marks. So the next question is how to characterize the marks. So marks is also characterized by some distribution. So, and it can be continuous or discrete depending on the situation. For example, if you think of the sentiment associated with the message, it's a continuous thing. So you can think that these marks can be some normally distributed random variable about some particular mean or variance. And if you think of whether you like or dislike, or even some topic of the post or something, so then you can think that it's a discrete random variable and follow some categorical distribution. So summarizing, one can think that time is characterized by an intensity function, which is lambda star, that is a likelihood that an event will happen between t and t plus dt given the history, and the distribution of marks, which comes from this m, and the joint likelihood of the actions is basically the product of intensity and marks, and the survival function, which takes into account of the fact that there is no event in between ti and ti plus 1 for all i's that you observed. And the next question is how to represent our problem in terms of MTPPs. So here, the actions that you want to determine. So you want to control this feedback process, okay? Or in terms of there is an underlying reward that you want to maximize. And you observe these feedbacks. Interestingly, we don't model this lambda star phi and m star phi. That is the point processes or the mark temporal point processes associated with these feedbacks. This is something that we don't try to model here. We don't have any assumption, and we don't try to model here. It's some kind of model-free reinforcement learning. But somehow, this is something that we want to learn. And we don't have any idea of what's going on in the feedback, and at each point of time we observe this thing, and we are taking the actions. That is, when the next event should happen, and what kind of event should happen. This is the thing at the nutshell we want to solve. So the representation learning model is the following. There are a lot of, the representation learning literature is very rich. So traditionally the agent acts and gets feedback from the environment, and feedback is usually the state, if it is observable, or some partially observable states, and then you get incremental reward, but just take into account that at each time step we don't consider the reward. We just calculate the reward at the end of the phenomena, that is at the end of each epoch. And the feedbacks and actions can be stochastic, and the final problem is to find the policy that an agent tries to maximize the reward. And then in the classical reinforcement learning problem, we usually consider a discrete setting where the action and state both are discrete, and you have continuous actions or state, but the events or the actions or state are taken at discrete steps. Rather, I should not say discrete time, but they're discrete steps. And there are other cases where the actions and feedbacks are both continuous signals, like in traditional continuous time control phenomena, you have some differentiable models and you try to design some PID-like control laws and so on. But what will be these situations where the actions and feedbacks are both asynchronous, they're marked temporal point process, and they're characterized by intensity function. So in a sharp contrast between from the existing work, our main contribution is that here the action is, or the policy is an intensity, and the policy is realized by sampling from the intensity. So it's not something that we directly tell that you should take this action, or you should take this action at next time step, or you should have a continuous function which is a kind of action. Rather, we design this intensity function, which is the policy, and we sample or we realize this policy by sampling from this intensity function. And interestingly, here we model the state as a history of the process. That is, at each point of time, the dimension of the state keeps on growing. So finally, we'll see that to alleviate this problem, we'll try to represent, or we try to embed this history into low dimensional vector, some kind of embeddings. So here we basically model this history as a state, and we embed this history as RNN. So this is the overall representation or architecture of this problem. So we have an environment which has both marks and times at each point of time, and then this time temporal differences goes to this this WT and BT, which is weights and bias, and then there is an agent that is taking actions depending on the environment's marks and this times. And interestingly, we both embed the marks of this agent and this environment with a common function, with a common embedding function. The purpose is that it substantially reduces the training time, and at the same time we try to, because we don't know how they influence the action and environment, or the temporal point processes involved in both agents process and environmental process, how they influence the entire dynamics is completely unknown. That's why we try to incorporate both in the same latent embeddings. And we have an embedding event source, which is from this timeline of events. And finally, we try to model this policy of the agents as an intensity function, and which depends on the history, that is the embeddings, and some increasing or decreasing intensity. And note that we explicitly model this as an exponential function to ensure that the intensity is always positive. You can also use sigmoid function, but the problem with sigmoid function is the following. The sigmoid function is basically since it is bounded, the problem is when you integrate that thing, and if you have sometimes this this lambda WT is negative, you end up getting a finite number of events. That means you have a finite sample to train, and that often creates the problem that you will not get a very good quality of estimated parameters. So you have to make sure that the integral of lambda t is always goes to infinite. That makes sure that the expected value of the number of events that you had in the in the action space or the feedback space is always very high. So that will help you to capture the phenomena better, and at the same time you will simulate more and more number of events to to get better estimate of your parameters. And this is the distribution of the marks if it is discrete. So it also depends on the history. So it's a basically categorical distribution. It's kind of softmax, you can see that. And this VC and VY are these associated weights. And these are the trainable parameters, that is VY, V, W, B, and etc. And this distribution of action may change because of this incoming feedback. So when you are going to sample the phenomena, suppose you at any point of time you decide to sample that you are going to post at after 5 minutes, and you suddenly discover that a new event has arrived. So then you have to make the sampling process again corrected, but you have to be faithful with the process. So this sampling process is a little bit complicated, but we propose a sampling method which is variant and unbiased, and I mean, for detail you can see the paper. So the idea is that basically you sample a random variable time at some point of time, and then this random variable indicates the next time that you are going to post. But at some point of time you may discover that a next event has already happened before you have reached at that particular time. But the sampling time that you have calculated doesn't take into account that you have that the new event is going to come. So you have to make this process self-corrected, and then you have to again compute the next time event. Okay, so summarizing, so this is a new RL technique to control marked temporal point process, and it embeds the state, which is the history of the associated with the marked temporal point process, into finite dimensional vectors, and we design an efficient and unbiased sampling procedure to handle asynchronous feedback. And more importantly, one of the departure of this from the prior work is that here the action or the policy is basically intensity, and we try to sample sample events from the intensity. So the policy is realized by sampling from the intensity. So the next question is how to optimize the policy, or how to calculate the policy. That is how to calculate the intensity function. So the idea is very simple. So you have basically this objective function that you try to maximize with respect to both actions and events, which are stochastic, and this R star means that it depends on the history. So you try to maximize with those things. Interestingly, you don't know this FT and P star, so you simulate again and again from the model that you have, and then try to optimize this function. And from the departure of the prior work is that there are a lot of works on this which consider this HJB and stochastic differential equations with jumps, which mainly assumes that the objective function is very well behaved, so that that can be solved in a closed form, and the dynamics is known. So that makes the task simple, and they give to that, and at the end you get like some elegant closed form solution, and that comes with guarantees definitely. But here we don't make any assumption about the feedback process. So first of all, we don't have any idea about the dynamics, what's going on in the hindsight. We don't have any, we know the reward function, but the reward function can be arbitrarily complex, but should be well defined. So this is the main power of this deep reinforcement learning adopted for this, developed for this marked temporal point process. And one can show that we can use this policy gradient method. So at each point of time, you can update this theta L plus 1, that is a parameter involved in this process, by just stochastic gradient descent. And we can apply the traditional reinforced trick. I should say that we have developed a new reinforced trick for these marked temporal point processes. So the reinforced trick for existing reinforcement learning technique that only takes into account of discrete random variables or continuous random variables. But in case the randomness is neither discrete or random, it's called some kind of random element because it's a random process induced by discrete events in continuous time. So you cannot model this as just discrete discrete events, discrete random variables or continuous random variables. But it turns out that this reinforcement trick holds true even for this kind of random element. So at each point of time, suppose you start with a some theta initial. So whenever you are calculating this delta nabla theta of g theta at any point of time, you simulate this simulate the entire process again and again and compute this likelihood depending on the theta, the updated theta at that particular moment. So the process is a little bit slow, but it is, I mean, this can be well defined, this is well defined and well posed and is computed easily. So, and note that this reward function can be arbitrary, and you can, as long as you know that, but we don't have any restriction of the reward function, and there is no to calculate the dynamics of or the parameterize the feedback process anyway. So basically, you just compute that. So you can see that it only depends on the actions. So you don't have to know the reward function. So you don't have to know the lambda. So you don't have to know the lambda of phi or the feedback processes anyway. So you can. It turns out that it only depends on the action process, and whose parameters you are trying to maximize, whose parameters you are trying to compute by maximizing the expected reward function at each point of time. So the underlying algorithm is the following. You can run any number of episodes for the policy. So the agent is simulated by sampling from the policy, and the feedback can be generated by from the observed events or by simulating the environments, and then finally you calculate the reward, then estimate the gradient and update the policy. And finally I come to this evaluation. First I describe this space repetition setup, that if you go, we have this Duolingo data, and this Duolingo is a language learning platform which wants to teach you like 50 words in 14 days. And then they schedule some lessons. The question is how to schedule. And there is a student that tries to, recall the word. We don't assume there is underlying student model. And the test score is computed at on the 16th day, that is the end of the episode. So basically the recall is after capital T plus this theta, that is the tau, that is the tau is 2 days. And so we can find this TPPRL achieves a high accuracy with respect to the existing algorithms that is memorize and this uniform. So memorize is a algorithm by us that has been published PNAS recently. So it says that so it assumes that the underlying function, that is the memory model, is known. The reward function is very simple, and we try to optimize that thing, and we get a closed form solution. But when you don't know that thing, but you have a complicated reward function, you get very substantially improved recall here. And you can see this even for difficult items, you can gain substantially well recall. It's not performing as good as memorize or uniform thing, but you'll get a substantial well recall. And in case of viral marketing, here the objective is that you want to gain your high visibility from the post, and average rank is calculated, that is rank of the post is calculated by the end of the campaign, and you are trying to minimize this rank. Okay, and the question is that when to post. So you don't post just by whenever someone is posting. You need not post just after oneself. You observe the rank and decide whether this person is a good poster or the person is clever enough to get high visibility, and depending on that you take the feedback. So we can see that our algorithm is more or less performing well, and by saying more or less performing well is that still we are not being able to catch one baseline, because this baseline is somehow knows the dynamics very well. As a result, it's performing very well, like this scrutiny. But its performance is better than Red Queen, which is another baseline. And basically, this Red Queen is in between this scrutiny and TPPRL in terms of the model knowledge and all. So summarizing, this is a new reinforcement learning method for temporal point processes that models the asynchronous rewards and actions with an arbitrary reward function. And the future work is that you can model natural gradient descent. You can do the same thing with natural gradient descent. So, and you can do multi-agent reinforcement learning and sort of. And the code and data is available in the GitHub. If you look at the paper, we'll find that link. And now I'm happy to take questions.
Okay, if there is no other question, let's thank Abir for the excellent talk.